All right, thank you. Yeah, hi everybody. My name is Joe Binder. I'm a student of Joseph Scalia and Jeffrey Neiman. And today I'm going to discuss a method in which I'm helped to develop to measure and predict moisture variable soil strength. So the motivation behind this study is to produce fine resolution maps of soil moisture and soil strength, which are useful for a broad range of applications. Spatial prediction of moisture variable soil strength is really important for predicting the trafficability of vehicles across terrain. However, many of the current vehicle trafficability models currently rely on empirical inputs that don't directly relate to soil strength parameters. And as a result of this, it's difficult to predict soil strength based on remote sensing data. So the objective of this study is to develop a method to measure surficial soil strength in order to parameterize and verify moisture variable soil strength based on remote sensing data. The model that we are hoping to parameterize and verify is called the stress model. It stands for the strength of surface soils. So this model calculates soil strength properties based on soil texture from remote sensing data and soil moisture from a program called EMTBS, which we will go into on the next slide. So soil shear strength is characterized by two primary parameters, which are cohesion and friction angle. Friction angle is a material property which varies with percent of sand, silt, and clay. And moisture variable cohesion has two parts combined into one. Part of it is effective cohesion, which is a material parameter, which varies with percent sand, silt, and clay, and apparent cohesion, which varies with moisture content in the soil. So if you imagine a soil that's saturated, as that soil starts to become unsaturated, as it loses water, it develops a negative pore water pressure or a suction, which adds to the total effective stress between soil particles, which increases the shear strength between those particles. So keep in mind that as the soil is becoming unsaturated, strength is increasing. So in order to get a moisture content, we use the EMTBS model, which stands for equilibrium moisture from topography, vegetation, and soil. So the model inputs consist of a coarse resolution soil moisture, which is typically on the range of 9 to 30 kilometer grid cells, which is not applicable to many applications. But using fine resolution topographic data, fine resolution vegetation, and fine resolution soil data, the program conducts a water balance of the hydraulically active layer, taking into account infiltration, deep drainage, lateral flow, and evapotranspiration in order to produce a map of fine resolution soil moisture. So from this, the stress model takes the soil texture data from remote sensing and estimates an effective friction angle and effective cohesion. Remember, the effective parameters are the parameters that describe material properties, hence why they vary with soil texture. The stress model then takes apparent cohesion estimated from a set of equations using EMTBS for water content to get apparent cohesion. The model combines apparent cohesion and effective cohesion to output a moisture variable cohesion and a friction angle. The problem with the model is its performance is hindered by a lack of soil strength data in order to predict those parameters that are determined by soil properties. So soil strength data, why it's important is vehicle mobility models use soil strength data as an input in order to predict the trafficability of vehicles. For example, the NATO reference mobility model, or NRMM, predicts trafficability based on terrain type, moisture conditions, terrain roughness, and vehicle geometry. So the quality of inputs really is important on the quality of outputs of these models. Traditionally, these terramechanic models or vehicle mobility models use soil strength data collected from a cone penetrometer. The test is performed by a small cone pressed into the ground at a constant rate as readings are taken incrementally. Using these readings, you can calculate what is called a rating cone index, or RCI. The rating cone index, it's a single value that is empirically related to a vehicle's trafficability based on the soil type and moisture conditions in which the cone penetrometer test was run. So the RCI, since it is a single value, it groups several soil strength parameters into one value, making it relatively rigid to adjustments for soil moisture. Another test that has been considered for vehicle mobility inputs is triaxial testing. It is conducted by collecting an in-situ sample of soil, extruding it in the lab into a latex membrane, making sure that membrane is watertight to the environment, placing a pressure cell around the membrane. Let me get my pointer out here. So this is the soil with the latex membrane, and then this is the pressure cell around the latex membrane, both which are inundated with water. So the advantage of this test is using this pressure panel here, you can individually control the stresses acting on the soil and the stresses within the soil. It is tried and true for traditional geotech applications, but it has been questioned to its applicability for vehicle mobility applications. Its shearing method is conducted by pressing this piston down to get a friction angle and cohesion. However, it's argued that this is much different than vehicle mobility applications. It is also very time consuming and expensive. It can take several weeks or longer to conduct and upward of $3,000 a test. Preparation is difficult and samples are easily disturbed, yielding inconsistent results. So the bevameter, or Bekker Value Meter, aims to more accurately represent stresses that the soils are feeling in representation of vehicle stresses. The bevameter conducts two tests, which are the pressure sinkage test and the rotational shear test. The pressure sinkage test is conducted by pressing plates of different diameter into the soil at a constant rate, and the force required to advance those plates is recorded. Using this data, you can calculate what are called Bekker-Wong parameters, which are empirically related to a vehicle's static sinkage on the soil. The test that we're more interested in this study is the rotational shear test, which is conducted by placing a shear annulus or a shear ring, shown right here, on top of the soil and loading it with a normal stress. It is then rotated at a constant rate, and torque developed in the rod is collected in order to generate shear stress versus shear displacement plots. The advantage of this test is it more accurately represents the stresses by a soil, and the CSU team currently has two bevameters. One, which is the field-focused bevameter, shown on the bottom left. It is human-powered, and the normal force is supplied by dead weight, so it's easy to take into the field. We also are developing a fully automated bevameter, which we hope to have completed here soon. So again, the data that is generated by the bevameter shear test by the shear annulus shown in the last slide is shear stress versus shear displacement plots. So it is run 3 separate times at 3 different normal stresses. And during each test, you can plot and calculate a maximum shear stress, which is defined as the shear stress at failure. This shear stress at failure can then be plotted against normal stress for the 3 tests in order to fit a line, and using Mohr-Coulomb failure criteria. For those of you who are familiar, you can calculate a friction angle and cohesion. And while the bevameter has been around for a long time, over 50 years, it still has limitations, and those limitations are generally misunderstood, and we're not sure how these impact soil strength measurements. So in the research that I'm doing, we're aiming to understand these limitations a bit better and see how they impact strength measurements. The first of which we seek to tackle was slip sinkage. Slip sinkage is defined by, again, if you remember that shear annulus is rotated for testing, and as it's rotated, it turns out that it sinks quite a bit into the soil due to an unbalance of forces acting on the failure plane. And so in order to calculate shear stress, we need to know the area that the failure plane is acting on. But since there is the production of this failure plane that is not against the shear annulus, it's impractical to determine its location and magnitude, therefore making it impossible to calculate a shear stress. So it has been proposed by researchers in the past in literature that sinkage should be reduced by loading the soil around the shear annulus, in theory returning the failure plane back to the shear surface. But there's minimal understanding to the magnitude and orientation of the surcharge and how it impacts the failure plane and shear strength parameters. In this study, we also used varying shear interfaces to study how they affect slip sinkage. So in efforts, again, to reduce this effect of slip sinkage, we first conducted studies on shear surfaces. This image on the lower left is the method that's traditionally used. They're grousers placed into the sand and sheared, or the soil and sheared, I'm sorry. The next method that we test was epoxied angular sand and sandpaper. We also tested the impact of internal and external surcharge on sinkage and how varying magnitude affected sinkage. The results of this study found that grousers actually had the highest amount of sinkage, followed by angular sand, with sandpaper having the least amount of sinkage. For surcharge conditions, no surcharge followed by external surcharge had the most sinkage, with internal and external having the least amount of sinkage. So using this sandpaper with internal and external surcharge to reduce sinkage in efforts to return the failure plane back to the shear annulus, we conducted varying surcharge levels for the internal and external surcharge. We found that with no surcharge, we had high levels of sinkage around 20 millimeters. However, with the introduction of small surcharge, sinkage was greatly reduced. It was determined, though, that with increasing surcharge, the effects of sinkage were relatively unchanged. So in efforts to reduce the material and excess dead weight for field testing, an optimum surcharge of 2 kPa was determined for future procedure. Using this altered procedure, using sandpaper with internal and external surcharge of 2 kPa, testing was conducted on the shear zone to better understand where the failure plane is lying. So a strip of fine black sand was placed into a well-graded sand shown in this image, and the bevameter was placed on top and the rotational shear test was conducted. Afterwards, the mixed sand was removed until the black sand was revealed again, and this depth of the black sand was compared against the original height of soil and the sinkage of the shear annulus. So from this, we have now a better understanding of where the location of the failure plane is in the soil, and we are also able to better understand how large of a sample size is required for laboratory testing. From this, the revised bevameter procedure, to reiterate, now conducts the test using sandpaper as the shear interface with an internal and external surcharge of 2 kPa and a reduced sample size required for laboratory testing. The future work of the study aims to produce a data set using this revised procedure in order to improve the performance of the stress model. We also have a field site that we have done some field testing in the past, and we want to go back out there with the revised procedure in order to validate and see how the stress model is performing. Again, to tie everything together, the EMTBS model is a very powerful tool that's used to downscale soil moisture from coarse resolution to fine. The stress model is then able to take soil composition and this downscaled soil moisture in order to produce maps of soil strength, specifically moisture variable cohesion and friction angle. The purpose of this study and its benefit to the stress model is with the production of a data set and an improved method for soil strength measurement, we'll be able to hopefully improve the performance of the stress model, therefore making the performance of thermomechanic models that predict soil strength, that predict the trafficability of vehicles better. Thank you, and if anybody has any questions, I'd be happy to answer.
Great, thank you, Joe. So you can feel free to enter questions into the chat queue or raise your hand and I will turn your microphone on. Give it a couple moments here, see if anything pops up.
All right.
Hi, Joe. This is Tim Green.
Hey, Tim. How's it going?
Good. Thanks for your talk. That was very interesting. I'm curious to know what you're learning about how soils behave at different moistures, because as they get dry, those surface soils really have very little shear strength, I think. Essentially, they act more like a bunch of individual particles with no cohesion. So how does that knowledge that you're gaining affect how you take these measurements and really go past the failure point of most soils, right?
Sure. Yeah, so it's that's actually referenced a lot in the literature, and it's been talked about that there is a zone of soil, since in situ it's layered, that it's the critical layer for strength measurements. So going forward, the bevameter would be used in cooperation with the rating cone index by the cone penetrometer in order to determine that critical layer to determine soil strength there. So for example, at the field site, we would remove that real loose surficial soil that you're talking about down to the critical layer in order to determine the soil strength layer that's dictating. Does that answer your question?
Yeah, that does. That makes a lot of sense to me, because yeah, your wheel track strength is going to be determined by probably a subsoil. That makes sense.
Sure.
So whenever you can get out there after the snow, you should have good moisture conditions.
Awesome. Great. Thank you.
Take care.